Hello, my name is Maxim Yang, and I'm head of R&D for DevOps technologies and cloud solutions at Bank Center Credit. The topic of our presentation, hybrid architecture for generative AI to meet regulatory needs. Before we begin, a few words about Bank Center Credit. The bank, one of the leaders of the banking system in Kazakhstan. The bank has 20 branches and more than 150 offices, serves over 3 million clients, and provides a wide range of services for private individuals and business clients. And also, we subscribe for 2 outpost racks in Q1 2024. Let's start with why we decided to use clouds and what our goals were. All of IT infrastructure was hosted locally into our own data centers, but with growing business needs and limitation for local solutions, we decided to scale our resources using cloud. Since different providers have their own advantages, we chose a multi-cloud strategy. What goals did we see in using clouds? First goal is flexibility and scalability. And second, innovative and competitiveness. Third goal is reliability and fault tolerance. And fourth goal is economic efficiency. But at the same time, as a bank, we need to ensure compliance with regulatory requirements. First requirement is data transmission and storage must be encrypted, and the encryption key must be stored in the bank. And second requirement is ensure anonymization customers' data during collection and processing. Based on these requirements, we start our journey to cloud with AWS Outpost. AWS Outpost is local private AWS cloud that stored in customers' data. We were one of the first in Kazakhstan who located this solution, placing racks in our own data centers, thereby all necessary requirements. We started exploring and deploying basic managed AWS services in this solution as managed virtual machines, Kubernetes, Basis, and S3 storage. The bank's application architecture core layer consists of Kubernetes-based microservices. However, this workload was already quite large, more 20 clusters, and we want to explore how we can migrate these workloads using cloud. We start exploring and deploying managed Kubernetes on AWS Outpost, and later integrated it with our internal bank services. And later, we approve this same deploying with AWS and other clouds, and as a result, we got the following diagram. This slide shows multi-cloud microservice architecture for Kubernetes clusters that's located in our data centers, in Outposts, as well as AWS Cloud and other clouds. All of this combined with centralized tools for deployment, management, and logging and load balancing. Returning to the requirements for cloud usage, we will discuss more about encryption implementation. For encryption, we used AWS KMS encryption service. He has a feature, external key store, XKS. And this feature allowed us to use local keys for encryption in cloud, and now AWS KMS cloud service can use our local keys. This solution allowed us to use our local keys for encryption in data in services in cloud. And it also used XKS proxy that is used for local keys can be transferred to cloud, to encryption service. And in our case, XKS proxy is located in our AWS Outposts. More about XKS. XKS is based on principle of double encryption. In the cloud, encryption service AWS KMS uses data key to encrypt data in AWS services. And in additional encryption, a root key is used that is located in our local on-premise. This key is an external key, and it is more secure, and we use it for our implementation. And so, bank was interested in AI and ML managed AWS services and GPU workloads for our projects. And we continued integration based on this encryption realization. And we made architecture for AI model training. This slide shows you architecture of model training of our ACR models. To do this, we made it synchronization between S3 Outpost to S3 Cloud. You can see step 1. After that, data can be training in the cloud on EC2 GPU or SageMaker. You can see step 2. And after that, the processed data can be transferring back from S3 Cloud to S3 Outpost. And finally, step 4, our internal services and services in EKS can interact directly with processed data. And all of stages, we use our local keys for encryption in data processing, transferring, and storage. After this, we continued integration with another service of machine learning. Its name is AWS Bedrock. And in this case, our local services and services in EKS Outposts can interact directly with API agent Bedrock, our private endpoint secure connection. And this it used in real time. And its solution allowed us to use all AI models that we can use in Bedrock. And this solution allowed us to scale our workloads to any sizes. And also, in all stages of data transferring, preparing, and storage, we use our local keys for encryption. And so, as a result, by implementation this architecture, integration, and encryption mechanism, we have created a technological foundation for our projects using AWS cloud services. That's all from me. Thank you. Alexander will tell you more about data anonymization and the implementation of real cases in bank. And thank you.
Yep. Hi there. My name is Alex Bernatsky. I'm a solution architect in AWS. And in the next 10 minutes, I will tell you about 2 generative AI use cases, which Bank Central Credit, or BCC, built on top of the hybrid architecture, which Maxim just showed you. But before, I must admit that I was just an advisor for this project, and most of this brilliant job was done by the data science team of the bank. Unfortunately, guys couldn't join us today in the full numbers, but we have Daria from this team. Daria, kudos to you and to your amazing colleagues. Thanks for being with us. So, I will tell you today about 2 cases. First one is fine-tuning of ASR model. ASR stands for automatic speech recognition. And the second case is implementation of internal HR bot to assist BCC employees. We'll start with the fine-tuning. So first I will explain you the reasons why bank decided to create custom model. Then I will show you the schema and will describe you the process, how actually fine-tuning was performed. And then I will show you the results and some quantitative metrics. So there are, in general, 2 reasons why bank decided to create a custom model. The thing is that majority of population in Kazakhstan speak Kazakh language. There are also a significant part of the population which speaks Russian. But there is also a third option, so-called mixed languages, when the person speaks Kazakh and Russian at the same time, like 2 words in Kazakh and 1 word in Russian. And you can imagine that there are models on the market, I mean ASR models, which can process the Russian language pretty good. Also, some of them can work with Kazakh language as well. But there is no model on the market which can work with the mixed language. And the first reason for the bank was to create this model for the mixed language specifically. Then, BCC stores the real data recordings, call center recordings, with 8 kilohertz frequency, which is quite good if you want to save the storage. But the thing is that most of the ASR models on the market, commercial or open source, they are trained with the training data sets with 16 kilohertz. And again, you can imagine that model trained with the 16 kilohertz doesn't really perform well on the 8 kilohertz data set. Furthermore, Kazakh language is so-called low-resource language. It means that if you search in the web for Kazakh language training data set for the ASR models, you will find just 2 data sets, both in 16 kilohertz, by the way, and they are not super rich in terms of vocabulary and features. So the bank decided to create its own custom data set with 8 kilohertz and with enriched vocabulary based on the real call center data recordings. That's the reason number 2. And that's the schema, how the process looks like. So I will guide you through the process. Initially, all call center recordings were stored in a Hadoop cluster on-premise and BCC data center. Then, each and every call center recording file was split into 2 channels, for agent and for customer. And then each of the channels were processed by a voice activity detection. It means that bank get rid of all the noise and all the silence in these recordings. And then these fragments, only with the voice, were split into chunks. Each chunk with variable duration from 2 seconds to 20. Depends on the duration of the actual phrase. And then each of these chunks were processed by a speech-to-text model, the previous version of the speech-to-text model which bank had at that moment. And it gave the bank the text representation of this audio file. So we now have audio recording and the text. Then both of this data, both of these files, both of these data formats were transferred to the outpost from Hadoop cluster to the outpost. Important question. Why bank didn't do all the pipeline on the outpost? The thing is that BCC outpost configuration doesn't have GPUs. We can provide the outpost with a GPU, but that's not the case of the BCC outpost. And for the speech-to-text model, you need a GPU. So bank has certain amount of GPUs. It's enough to do medium-size models. It's enough to do an inference for these models, but it's not enough for the fine-tuning. So they use the GPU power to launch the previous generation of speech-to-text model to generate text, and then put everything to outpost, audio and the text both, and then processed text files with the name entity recognition model to identify all personal information and sensitive data and confidential data in the text files. It was the hard requirement from the internal security that none of this data should leave the security perimeter of the bank. So, and all the chunks, all the files where this data were identified was removed from the training data set, both text files and the audio file. And now, bank had, it's the step number 3, by the way. So now bank had audio file and the text files, both encrypted in the way like Maxim said with XKS internal keys, and also cleansed from all personal data and sensitive data. Then it was converted into special format called MEL spectrogram. If you never heard this word before, don't panic. I will explain it on the next slide. Just keep it in mind for a while, OK? And so these MEL spectrograms were transferred from the S3 on outpost to the S3 in the region. Again, encrypted with external keys, without the sensitive data, fully compliant with all the regulations. And MEL spectrograms, by the way, it's not audio, it's not a text, it's something very specific. I'll explain it. And these MEL spectrograms were served as the training data set for the fine-tuning job in a SageMaker AI. And this fine-tuning job resulted in a certain number of model artifacts. And these artifacts were returned back on premise and then hosted for inference using the local GPU power. So bank used our cloud power, our cloud GPUs for the fine-tuning, and then take the model back on premise and host it for inference on premise. That's the process. So what is MEL spectrogram? MEL spectrogram is literally an image of the audio. And the data scientist can get this format from audio file by applying Fourier transformation on top of it, and then also apply a MEL scale on top of the Fourier transformations. And it gives us, and gives data scientists, the bidirectional representation of your audio when we have axis X, which is time, and we have axis Y, which is frequency, and we also have a color, which is amplitude. And this is, by the way, kind of a best practice, how data scientists prepare the data set for the ASR model. And BCC followed these best practices. So results. As you can see, results are pretty good because for all 3 languages, bank achieved significant accuracy improvement. It's, how many, 9% for Russian, it's 15% for Kazakh, and what is the most important, the most significant improvement for the mixed language, which was the major goal, right, for, to do a custom model. It's 23% for the mixed language. And furthermore, this model appeared to be more cost efficient than the previous commercial ASR solution that bank used, and it allows bank to save 4 million tenge every month. Tenge is the local Kazakh currency, if you don't know. So now this model works as a part of post-call analytics pipeline. This project considered to be successful, and bank planned to scale it further in the next year. To next case, HR bot. There are several reasons why bank decided to implement HR bot. Reason number 1 is to improve quality and velocity of HR responses. The reason number 2 is to stimulate the self-service culture in a company. And the reason number 3 is to refocus the HR employees to more strategic initiatives rather than some routine duties. And of course, this chatbot is supposed to be compliant with internal and external regulations. And it means that none of bank confidential data should leave the security perimeter and on-premise security perimeter. That's why bank used the technique which we call the hybrid RAG. RAG stands for Retrieval Augmentation Generation, pretty famous thing. I think you all know what is it, right? And by using RAG, we kind of supply additional context to the model. We provide the knowledge which model doesn't have out of the box, and this knowledge is the internal HR policies of the bank. And as you can see from this schema, initially the HR knowledge base was processed by embedding model using the local GPU power, and then resulting vectors were stored in the Postgres database on Outpost, because Postgres can be a vector database. I hope you know it. And the same process was applied to the user prompts. Obviously, chatbot has UI, and when the user types in the prompt, this prompt goes to embedding model converts it to vector, vector goes to the Postgres, then the vector search works, and it results with additional context from the Postgres vector database, which is actually additional context from knowledge base. It added to the initial prompt of the user, and then prompt plus extra content sent to the cloud, to the region, from Outpost to the region, to the service which we call AWS Bedrock. In Bedrock, we have model, Cloud Sonnet 4.5, I think, at the moment. And then model processes the prompt and additional context, provides the response, and send response back to the chatbot on premise. That's the process. Regarding the results for the chatbot, according to the bank assessment, now roughly 70% of the HR request goes through this HR bot, which is quite good. That's definitely allowed it to reduce the workload of the HR team. And what is even more important, bank collected the feedback from the employees, whether they're satisfied with the chatbot or not, and feedback is mostly positive. This is super nice. So, we would like to give you key takeaways from our session. First, Max, regarding the platform.
First, we built a secure hybrid multi-cloud platform that complies with legal requirements and they're tailored for bank business needs. And second, implemented flexible, scalable, and cost-effective architecture that enables an innovative approach and high competitiveness. And second?
Good. And regarding the GenAI process. So the bank implemented the fine-tuning process for the generative AI model, for ASR model specifically. This process relies on the hybrid architecture with the key component of this architecture, Amazon Outpost. This process is fully compliant with internal and external regulations. And the bank considered to reuse the same approach for every other GenAI task to leverage the cloud GPU force for the fine-tuning and then use the actual model on-premise. And regarding the HR bot, with HR bot, bank created the successful example that GenAI can automate routine tasks. It set the footprint for the same project, and bank planned to implement the same project, but just in different functional areas like IT support or procurement. So that's all for us for today.